Hello everyone, a very good evening to all. Can you see my screen? Okay, so I welcome you again to the interaction session on atomic and molecular physics. Today, we basically will be covering the whole complete atomic and molecular physics that you have gone through in the past few months. So, myself Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So, today we will discuss. Today I will give you all an overview of the course Atomic and Molecular Physics. So you can ask any doubt if you have. So first we started with the structure of atom. We started with different experimental and theoretical verification of atomic structures. Then there was structure of atom explained by different models. Then first there was Dalton's model. Then after that there was Thomson's atomic model. First there was Dalton's atomic model. After that there was Thomson's atomic model. Thomson's atomic model and Thomson's atomic model basically it could not explain the stability of the stability of the atom, and there were many other demerits of the model that it can't also tell the different type of spectral lines that are coming in case of experimental results. So after that Rutherford Rutherford, he performed the Rutherford foil experiment, and from that he said that the atom is consists of a centrally placed positively charged nucleus, and the electrons are revolving around it. But again, he could not explain the distribution of electrons and other uh, mm, regions of stability of the atom and other spectral natures. So after that, a more detailed theory of atom was given by Bohr, and basically Bohr took the help of quantization, and from quantum mechanics, he said that atom consists of nucleus and positively charged nucleus which is placed centrally, and electrons are revolving around the nucleus in certain orbits which is known as energy states or stationary states. And he also said that the electron can revolve only in that orbit in which the angular momentum of electron is an integer multiple of h cross. So according to Bohr, according to Bohr, what he told, there is a sing in an atom, there is a centrally placed nucleus, and electrons are revolving around the nucleus in certain circular orbits. Though in my diagram it does not look circular. So, but you know the orbits are circular that were given by Bohr. And he said that an electron can revolve only in that orbit or stationary state in which the angular momentum of electron. Angular momentum is nothing but L, which is equals to mvr mvr, and that is equal to integral multiple of h cross, that is n h cross. You know h cross as the unit of angular momentum, so we can say that h cross or n h by 2 pi. So it was a type of quantization rule that Bohr used, and he was successful to explain a few properties of atom. And he also said that as long as an electron is revolving in the orbit or stationary state, it does not emit or absorb any energy. However, when the transition occurs, that is when the electron goes from higher to lower orbit or lower to higher orbit, then there is the exchange of energy. Either the electron emits energy or the electron absorbs energy. And when the electron emits energy, the frequency, the difference in energy, which corresponds to particular frequency or particular wavelength, then that results in the occurrence of or the origin of atomic spectra. So using this quantization, and again we the structure of atom we discussed, but and another thing was this was the one condition, and another condition was the regarding the stability. He said that the force of interaction between the coulombic force of interaction between the nucleus and electron, suppose electron is here and there is coulombic force of interaction as they are placed at some distance, suppose this is r, and this coulombic force of interaction is equal to the centrifugal force which is provided by the system, so that the electron is revolving around the nucleus. So we balance the two forces, that is centrifugal force. The centrifugal force is nothing but centrifugal force, we know centrifugal force given by mv square by r, which was equal to the coulombic force of interaction, that is k z square by r square, k z square by r square, where z is the atomic number of the Z is the atomic number, K is the K is constant, and you know all the other terms. R is the radius of the stationary state. So from that we derive different relations, that is velocity, radius, energy of the electron in a particular state, and we found that we derived Vn equals to Z square by 2 epsilon 0 NH, Z square by 2 epsilon 0 NH. Z square by 2 epsilon 0 NH, and similarly the radius of nth orbit was also the radius of nth orbit Rn was n square x square epsilon 0 by pi n Z square n square x square epsilon 0 by pi n Z square, and the energy is minus 1 by 8 n Z square e4 by n square x square epsilon 0 square. So these were derived for hydrogen and hydrogen-like atom, because the Bohr's model was only valid for hydrogen and hydrogen-like atoms. So if you can put different values for Z, suppose the hydrogen-like atoms are helium plus lithium double plus, like that. So we derived different values of velocity, radius, and energy. And from as I told you that the difference in energy is the cause of the the difference in energy gives rise to the spectral the spectrum. That is when the electron, the transition occurs for a electron from any higher orbit to lower orbit, or any lower orbit to higher orbit, the change in energy is reflected as terms of radiation. So from that it gave rise to atomic spectra. So we discussed hydrogen spectra, and hydrogen spectra, the hydrogen spectral lines if we consider, if you see the energy levels, then this is n equals to 1, then this is n equals to 2, and the difference between the energy goes on decreasing as we go to higher and higher values. So as we go to higher and higher values, the energy value will be, the energy levels are closely placed, and these energy levels, they have certain energy, like we know for n equal to 1, the energy is minus 13.6 electron volt, and for remaining levels, the relation is minus 13.6 by n square. So for 2, it will be minus 13.6 by 4, like that. So if you compare, the difference between these two is greater than that of the difference between these two. So like that, at infinity, that n equal to infinity, the energy levels are continuous. So these are the levels of hydrogen atom, that is the energy that occupied by the electron, because hydrogen is nothing but the but a bound state of proton, one proton which is present in the nucleus and one electron which is revolving around the nucleus. So hydrogen atom is a bound state of proton and electron, and that's why we are getting negative energy. We found in hydrogen spectra there are different series. So the first series, if the transition occurs from any excited state to n equal to 1 state, then it is called as Lyman spectra, Lyman series. Then for n equal, if the transition occurs from any higher excited state to n equal to 2 state, that is the fast excited state, then this is called as Balmer line. And this was Lyman, this was Balmer series. Then for n equal to 3, this is Pastian series. Like that. So Balmer series is only in visible region. However, the other regions lie in either ultraviolet or infrared region. You can see Lyman series. For Lyman series, the transition of energy, the transition of electron is from any higher excited state to the ground state, and you can see the difference in energy is maximum in case of Lyman series. So if you compare the difference in energy, and this, if we compare it to h nu according to the Planck's theory. So when you compare it to h nu, then you can find nu is very, very large in case of Lyman series. So for higher frequency, we have ultraviolet region, and for lower frequency or higher wavelength, we have infrared region. So Lyman series lies in the ultraviolet region, Balmer series lies in the visible region, and Paschen series lies in the infrared region. And there was a constant which was very important to analyze all these spectrums and the spectral. And the generally a spectrum is represented in terms of either velocity, either wave number or wavelength and frequency. So all these expressions contained a constant which was Rydberg's constant. This Rydberg's constant, we also did some problems which are related to this Rydberg constant. Its unit is centimeter inverse or meter inverse, and its value is 1.097 into 10 to the power minus 7 meter inverse. And this value, the value we have taken here is also represented as r infinite, because during this in this expression it contains m, which is the mass of electron only, but we know that the atom is a bound state of proton and electron for the hydrogen atom. So if we are considering only the mass of electron here, then we are neglecting the motion of the nucleus related to the electron, and or any other words, we can say that we are assuming that the mass of the nucleus is infinite. However, the mass of nucleus is not infinite; it has some finite mass. So due to some finite mass, there will be reduced mass, not the mass of electron, but there will be reduced mass. And when you put the reduced mass expression, you can find the expression for r will be the value of r will be decreased. So if you take for a finite mass, then the value of R will be less than that of the value we have derived for infinite mass of nucleus. So from these there are we can we studied about different atomic spectra. Then we found the mass correction and the Rydberg constant was modified. Then we discussed about vector atom model. That is the atom we discussed we introduced different quantum numbers and we said that when an electron is revolving in an orbit, then due to its orbital motion or speed motion, it produces different magnetic dipole. And electron, when revolves in a stationary orbit, it produces a magnetic dipole, and due to this magnetic dipole, it generates magnetic dipole moment. So since there are both orbital motions and spin motions of electron. However, spin was derived later on, but generally we consider the orbital motion of electron, and we know this is dipole moment, and dipole moment mu is equals to I into A, that is current into area. And when you calculate it, then we can found the ratio of orbital dipole moment to orbital angular momentum. This is mu L vector divided by L vector. Its ratio is equals to minus E by 2m, which is minus E by 2m, which is called this ratio is called as gyromagnetic ratio, which is the ratio which is the ratio of magnetic dipole moment to the angular orbital angular momentum. That is, if an electron is present in a state with orbital angular momentum of L vector, then how much amount of orbital magnetic dipole moment will be produced in that state. So it is, since electron is negatively charged, we are getting negative sign here in the right hand side. If you take magnitude, then it will be mu L by IL. Then if you take magnitude on both the sides, then it will be positive. So this is known as gyromagnetic ratio, that is T by 2n. Here there is another factor which is orbital g factor, which is equal to 1, and the unit of atomic orbital magnetic moment or spin magnetic moment is Bohr magneton, and Bohr magneton has the expression mu b is equals to P h cross by 2m e. So, like in atomic and molecular physics, we are calculating the magnetic dipole moment in terms of Bohr magneton. In nuclear physics, we calculate in nuclear magneton, and nuclear magneton, the expression is Eh cross by 2mp or mn, whatever it may be. And if you can see, since mass of proton is very greater than mass of electron, so the Bohr magneton is very greater than that of nuclear magneton. So you can say that Bohr magneton is nearly equal to 1836 times of nuclear magneton. Also, we in this vector atom model, we consider the different quantum numbers like L vector. Quantum mechanically, we can represent L vector. The value of L is L into L plus 1 root over into x plus, where x plus is the unit of angular momentum. So this was orbital angular momentum. Also, we found that like here the orbital angular or this value L can be 0, 1, 2 like that. There are different quantum numbers that came into picture where n was principal quantum numbers, then L came into the orbital quantum number that was 0, 1, 2, and its value was up to n minus 1. So these were the things that we discussed in vector and orbital. Also, like this, orbits are also quantized. Like with the orbital and the orbital quantum numbers have value 0, 1, 2, 3 like that. The orientation of the orbital, the orientation of the like the orbitals are quantized, the orientation of the these orbits are also quantized, which is known as space quantization. And the space quantization occurs in case of when the space quantization is found when we apply an external magnetic field. Suppose we apply an external magnetic field which is along this z direction, then the orbits it precesses around this magnetic field. Like orbit can be like that. If this is the orbit, then the L vector will be perpendicular to the surface of the orbit, and there is angle between them is theta. So the orbit gets oriented because due to the interaction between the magnetic field and the orbital magnetic moment that is produced due to the orbital motion of electron, the experience torque, and due to which the plane of the orbit gets modified. So this is known as space quantization, and for space quantization, there are different values of theta, and the values of theta we found that theta will be the value of theta will be cos inverse ml divided by L into L plus 1 root over. So here ml is another quantum number which was found in which is in presence of the magnetic field, and ml is such that the z component of orbital magnetic moment is that proportional to the z component of orbital angular momentum. Ml, what is ml? Ml has values from plus L to minus L, that is it has 2L plus 1 values, 2L plus 1 value, such that the z component of angular momentum will be ml h cross. So if you from these values, there's 2L plus 1 value. If L is equals to 1, then ml will have 3 value. These are minus 1, plus 1, and 0. So these are 3 values: minus 1, 0, plus 1, and these came into play in presence of an external magnetic field, and also the precision of this orbit is known as Larmor precision, and the frequency of precision is which is known as Larmor precision, and the frequency of precision is EB by 4 pi m. EB by 4 pi m, where B is the strength of magnetic field applied, m is the mass of electron, and E is the charge of electron. Then we must have studied about the Stern-Gerlach experiment, in which there was discovery of electron spin, and the electron is spin half particle, because from their experiment they found the orientation of the electrons to which collided the spin, they were split into two lines. So since there are since the experiment he performed, the orbital angular moment, the orbital quantum number was 0. So they found that there must be another quantum number due to which the orientation is occurring. So there are two spots, and we know that, like here 12 plus 1, we have 2s plus 1, since 2s plus 1 equals to 2, it gave s is equals to half. So the spin of electron was defined. The spin of electron and the algebra of the spin of electron is very similar to that of the orbital motion, but only there is one difference. Like in orbital motion, we are getting mu l by l, mu l by l. We are getting e by 2m, but in case of spin, mu h by h, mu h by h mod equal to Vs into T by 2m, where Vs is 2. So electron, the spin of electrons have two different orientations. That is, electron, they can be the spin of the electron can be spin up or spin down, like that, spin up or spin down. So there are two possible combinations, and due to it, their Gs is 2. That is, the G factor for spin is 2. And due to the evolution of due to the discovery of orbital quantum number and spin quantum number, we found that when these when a field magnetic field is applied, this quantum number they precise around they precise around the applied magnetic field, and due to the interaction between them, they form a new quantum number which is known as total spin, that is J. So we found there was a new angular momentum, which total angular momentum of electron, which is the summation of orbital angular momentum and spin angular momentum, and it was J vector, which was L vector plus S vector, and due to the discovery of this total angular momentum quantum number, there was fine structure of atom, and the fine structure of atom was differentiated into two types, that is LH coupling and JJ coupling. In one case, first, what happens in case of lower Z, when Z is very very low, that is lighter atoms. In case of lighter atoms, there are a few electrons present, and in that case, the individual spins and the individual orbital and individual spin angular momentums, they get added up to form the total angular momentum capital L. So if there are two electrons, suppose there are two electrons, here one electron, here one electron, it has orbital quantum number L1, it has L2, it has spin S1, it has spin S2. Then what will occur in case of coupling? First, the two orbital orbital angular momentums will be coupled to form a new total orbital quantum number, which is L1 plus L2 to L1 minus L2. Similarly, after that, two spins will be added. They will form total spin will be S1 plus S2 to S1 minus S2, and after that, this L and S, they will get added up vectorially, and they will produce the total angular momentum J. So a single line which was present in case of normal spectrum, we found that due to the introduction of these quantum numbers, that is the orbital angular momentum vectors, spin angular momentum, total angular momentum, the single spectral line got split into a number of spectral line. So this was the case for fine structure. So this is LS coupling, and in case of JJ coupling, what happens? In case of JJ coupling, uh, for heavier atoms, that is Z is very large, then in that case there are many electrons. So the interaction between the orbital and spin, that is more dominant than that of the individual interaction between the orbitals. So in that case, if the electron has L and S, then it will form a small j. Similarly, other electron which has another L and another S, it will form a small j, and these JJ they will form the total quantum number, which will be J1 plus J2 to J1 minus J2 with increasing 1. We have we have done many problems on these, like particular terms when there are two electrons present in P cell, that is or one electron in P cell, one electron in S cell, like that. So in case of LS coupling, you can see it is capital L and capital S, but in case of JJ coupling, it is small j. So this capital L means it is the combination of all individual L's, that is small L1, L2, like that, and the capital S is the combination of all spins, that is individual spins. However, this small j in JJ coupling stands for each individual electron. So in case of JJ coupling, the orbital and spin orbital and spin angular momentum, they are coupled due to the spin orbit interaction to form the total angular momentum quantum number, and this angular momentum quantum number they give rise to they give rise to the JJ coupling and the different spectral terms. And the spectral terms we note. And the spectral terms, we note the spectral terms in the form of 2s plus 1 Lj. This is known as spectroscopic rotation. Spectroscopic notation 2s plus 1 Lj. This is multiplicity. This is the uh, orbital quantum number, and it is total spin quantum number. So L value, for L value 0, it is S, 1 it is P, 2 it is D, like that. So this is the multiplicity, and there was a rule which is known as Hund's rule, and this rule signifies how the energy levels are arranged, and the properties of these rules are the a level which has highest multiplicity will be lying lowest, and for a particular, and for a sim suppose there is uh, high p and there is 3p. So since height is greater than 3, so it will lie fast, or that is, it will lie lowest, and then there will be 3. Then there will be 3p, and below it will be 5p. And if there are more than one levels with same multiplicity, then the one which has higher L value, it will lie the lowest one. Suppose one is 3p and another is 3d. In that case, both threes are equal, that is the multiplicity is equal. But for p, L is 1, and for d, L is 2. Since 2 is greater than 1, so 3d will lie lowest, and after that there will be 3p, like that. And also there are in order to arrange in terms of the total angular momentum quantum number j, we discussed that the lowest j value will be L minus S for less than half field case, and L plus S for more than half field case. Suppose we are considering a case of, suppose we are considering P5. That is, there are 5 electrons in P. We know P can contain 6 electrons. Since it has 5 electrons, then it is more than half filled. So for P5, the ground state will have J value which is equal to L plus S. J equal to L plus S. But if there is P2, that is 2 electrons present in P, then the ground state will have J which is equal to L minus S. So this is an important relation. You should remember this type of questions generally comes in entrance examinations, net gate tests, like these examinations. And also we found different spectral terms, the ground state of the spectral terms. Then we uh, discuss about quantum mechanical treatment of hydrogen atom and hydrogen like atom. And from quantum mechanical treatment, there were different. We solved the Schrodinger equations, and and you must have read about you must have read about the postulates of quantum mechanics, the Schrodinger's equation. In quantum mechanics, like in classical mechanics, we first find position, and from position we found velocity, and then acceleration, then force, like that. But in quantum mechanics, we obtain the wave function, and from wave function, by operating different operators on this wave function, we found the value where a cap is the operator and psi is the state. So in quantum mechanics, each state is represented by the wave function. So psi is wave function, and also the wave function, the nature of wave function we can found, that is the expression for wave function. Not all expression can be a wave function. There are different conditions, like wave function should be finite, wave function should be single value, like that. There are different conditions for wave function, and like in classical mechanics, we are acquainted with the equation of motion. We solve equation of motion. In quantum mechanics, we solve Schrödinger's equation, and this Schrödinger equation is nothing but h psi equal to e psi, h psi equals to e psi, where h is the Hamiltonian operator, h psi equal to e psi. Hamiltonian is equivalent to total energy. So when you operate this Hamiltonian operator, it will give the total energy of the system. And if you represent H in terms of kinetic energy plus potential energy, kinetic energy plus potential energy, and we know kinetic energy we represent in classical mechanics p square by 2m, but in quantum mechanics p has the form minus ix cross del by del x. So if you arrange, then x will be minus x cross square by 2m del square by del x square plus vx. So if you operate psi here, then you will get energy value, and energy is so in quantum mechanics, we found every physical quantity is associated with the operator, and when you operate the operator, then we found the value. And if you operate the operator in a state, suppose we operated the operator a cap in a state psi, and it gave some values a, and it again reproduced the same state, then this is known as eigenvalue equation. This relation known as eigenvalue equation, and this value a is known as eigenvalue, and this wave function psi is known as, this wave function psi will, the state psi will be called as the eigenstate for the operator a cap, which gave the value a. We have solved different problems regarding this eigenvalue. Suppose, for example, if you take sin x as the, if you take sin x as one state, suppose psi is sin x, suppose psi is sin x, and another operator a cap is del by del x. This sin x, the operator is del by del x. So when you do del by del x of sin x, it will give you cos x. Since the psi is getting modified to psi prime, then we can say that this is the, for operator del by del x, psi equal to sin x is not an eigenstate. But if psi exponential x, that is e to the power x, then if you take derivative of e to the power x, that will be again e to the power x. So in that case, the operator del by del x is an eigenstate of e to the power x, because e to the power x is again being produced. Similarly, if you use e to the power 2x, then its derivative will be 2e to the power 2x. So the eigenvalue is 2 in this case. So if you take the derivative, then the state is not being changed. The state is remaining constant. That is e to x, e to the power 2x. But the value is, but we are getting a new value which is 2. So 2 is the eigenvalue in that case. So from quantum mechanical treatment, we solve the hydrogen atom. We use the potential, like the potential here in Hamiltonian. We use the Coulomb force of interaction, and from the quantum mechanical treatment, we derive different solutions of the wave function of the wave function of the hydrogen atom, and we found that the wave function of hydrogen atom then is represented by n, l, m, where n is principal quantum number, l is orbital quantum number, and m is magnetic quantum number. Because this quantum number is this quantum number comes into play when there is an external magnetic field. So this was some there was an expression for psi NLM, which when you solve the Schrodinger equation, then this psi is the solution of the Schrodinger equation, and this represents the state of the atom. Then we found different expectation values, because in quantum mechanics the values are not exact. We always find the average or expectation value of a quantity, and the expectation value of a quantity is generally how it is calculated. The expectation value is generally calculated in. So the expectation value is generally calculated. Suppose psi is a wave function, and if you calculate the expectation value psi in a wave function psi, or suppose you want to calculate the expectation value of a quantity A, so expectation value of A is represented in like that. It will be psi A psi divided by psi. Psi, this is a type of notation which you know that Dirac's bracket notation. But if you do it in terms of integration, it will be integration psi star A cap psi for one dimension, or we can say dx, divided by psi star psi dx. So this is the formula for expectation value of a operator. So this was quantum mechanical treatment of hydrogen atom, and also we discussed few things in quantum mechanics. Then then we studied the G-man and Stark effect. Like if an atom is placed in an external magnetic field, then spectral lines get splitted, and it is due to the interaction between the magnetic field and the intrinsic magnetic moment that is being produced due to orbital and spin motion of electron. There are two types of, suppose in case of magnetic field there was G-man effect. In case of magnetic field there was G-man effect, and G-man effect are two types. One was normal G-man effect and another was anomalous G-man effect. In case of normal Riemann effect, one single spectral line was being splitted into three lines, but in anomalous Riemann effect, it was splitted into more than a number of lines. There is not a particular value. And for normal Riemann effect, we found for normal Riemann effect, the state S was for the state which was normal Riemann effect. For it, the state S was 0 or L was 0. Like there are only one of them is 0, so there is no interaction, and only we are getting three one spectral line is being splitted into three lines. However, in case of anomalous Riemann effect, what happens? Suppose in the normal Riemann effect, there is S is equal to 0, and we have L equal to non-zero. L is not equal to 0. Then a single label will be splitted into 2L plus 1 labels. And the selection rule for transition was delta L was 0 and plus minus 1. So delta L 0 gave one series of line, delta L plus 1 gave another series of line, and minus 1 gave another series of line. So there were three lines. However, here in this case, since there is L and S both are non-zero, so there is LS coupling and J is produced, and due to J, a single spectral line is splitted into 2J plus 1 label, and according to that, there is the selection rule was delta Nj was 0 plus minus 1, delta Nj was 0 plus minus 1, where 0 to 0 is not allowed. But since there are, like we discussed, there was GL, GS, there was another value which is known as Landé G factor, which is Gj. The value of GL was same for all the states. GL was 1 and GS was 2. But here the value of Gj is not same. It depends upon the quantum numbers L, S, and J for a state. So since the value of L, S, and J for a state are different, for different states they are different. So the value of Gj are different, and this value of Gj gave rise to different energy gaps. And due to this, thus in anomalous Riemann effects, the splitting of the spectral line is into a number of lines. And in case of electric field, then due to the force applied due to the external electric field, the spectral line is also splitted. and we found there is linear Stark effect in electric field. This is known as Stark effect, the splitting of spectral line in external electric field known as Stark effect, and it is also different type. One is linear Stark effect, another is quadratic Stark effect. If the if there actually in Stark effect there was the introduction of a perturbation theory, which is an advanced quantum mechanics. So due to it, if the perturbation, if the perturbation means basically it is small disturbance in actual condition. If there is a small disturbance, then we call it as perturbation. And if the change or disturbance is linearly proportional to electric field, then it is known as linear Stark effect. And if it is proportional to the square of electric field strength, then it is known as quadratic Stark effect, like that. So you discuss about the atom. We discuss about the atom which is present in external magnetic field or electric field. Then there were molecular spectra, and we found that uh, uh, due to the intrinsic dipole moment, if the atom has intrinsic dipole moment, then it shows rotational and vibrational spectra. And rotational spectra we found, in case of rotational vibrational spectra, we found that for electronic spectra, each electronic level consists of different vibrational levels. Suppose this is electronic level, it is 1, 2, 3 like that. Then each electronic level consists of different vibrational level. So it will be V equals to 0, 1, 2, 3 like that. Also it will be again V equal to 0, 1, 2, 3 like that. And each vibrational level it consists of a number of rotational levels. So each vibration level consists of a number of rotational levels, and they are represented by J equal to 1, 2, 3 like that. So if a transition is occurring from this one electronic level to another electronic level, then it gave rise to electronic spectra. And if the transition is occurring from one vibrational level to another vibrational level in same electronic spectra, that is known as vibrational spectra. And if the transition is occurring such that the rotational level corresponding to one vibration level, the transition is occurring from a rotational level to another rotational level corresponding to another vibration level, it is known as uh, rotational vibrational spectra. So we have pure rotational spectra, and we have rotational vibrational spectra. So we solve different problems related to rotational spectra and vibrational spectra. And rotational spectra, we found there was a rotational constant which was B, and its unit was length inverse or centimeter inverse. Then we calculated B, and we know B was inversely proportional to the moment of inertia, that is I. So we can say that B is inversely proportional to moment of inertia, or B is inversely proportional to the reduced mass. Then we solve different problems which are based on the reduced mass. Suppose the bond length was, suppose this was Cx, the bond length was given, but we had to find the mass of X. So like that, because if the bond length has given, there must be mm, the value of b given, because we know all the values, but in I we know mu into r square. We know the value of moment of inertia is mass into distance square. So in this equation, I equal to mu r square, only one unknown is mu, because r is given to us, r is the bond length. So from this we can calculate mu, and we know if there are two masses, the effective mass is m1 m2, m1 into m2 divided by m1 plus m2. So we solved different problems which were based on the reduced mass. And again, the rotational spectra was for rigid rotator and non-rigid rotator. In case of rigid rotator, what we found? In case of rigid rotator, we found that the energy levels are not equally spaced, but the spectral lines are equally spaced. The energy levels are not equally spaced, but the spectral lines have a gap of the spectral lines are equally spaced, and the gap between them is 2b. So if in a question there in the if in a question it is given the spectral lines are separated by a distance of something, then you can say the 2b value is given. Then from the value of 2b we can find the value of b, and again if we know the value of b, if either of the effective mass or distance between the two atoms are known to us, then we can find out the value of the moment of inertia or effective mass like that. So also in case of non-rigid rotator, we found that for non-rigid rotator, the spectral lines was unequally spaced, as well as the energy levels are also unequally spaced. And in case of after the rotational spectra, then we discuss about vibrational spectra, and in vibrational spectra, um, we consider the vibration of a, in case of vibrational spectra, like in rotational spectra, we are discussing about the rigid rotator. In case of vibrational spectra, we discuss about the simple harmonic oscillator, and the energy levels are given by, if V is the quantum number associated with the vibrational levels, and the expression for energy is n plus half h cross c omega e, where omega is the vibrational constant and omega is 1 by 2 pi into k by mu. So from the relation we can say that the energy levels, because if you say here it will be 1 by 2, 3 by 2, 5 by 2 like that, so the separation between the two energy level is equals to h cross c omega e. So the spectral lines, though the energy levels are equally spaced, and we get a single spectral line. But if you introduce an anharmonicity, then in that case the energy of the state will be changed, and it will be n plus half h cross c omega e minus, suppose it is not n, it is v, because for vibration we take v, so it will be v plus half square, and the remaining terms are h c omega e x c, where x c known as the anharmonicity, and this anharmonicity depends upon the mass. And due to this anharmonicity, we found there is fundamental vibration, there is fast overton, second overton like that. Then the uh, in case of if the these were for pure rotational, pure vibrational spectra, the spectra can be again rotational vibrational spectra, because if you consider the transition is from rotational level of one vibrational line to another rotational level of another vibrational line, then that is known as rotational vibration spectra. They are not pure, and we found that there are different series, they give pqr. So this is q for this is r, like pqrs like that, o pqrs. So it is for it is plus minus 1, it is plus minus 2, the transition will be plus minus 1 plus minus it is plus 1, it is minus 1, it is plus 2, it is minus 2 like that. So these were the spectral series that we found. Then at last we discussed Raman spectra. So the in case of Raman spectra, what we found, Raman spectra, when the electromagnetic wave incidented, then the we got three different series. One is the original frequency, another is with higher frequency, and another is lower frequency. So if you arrange in terms of frequency, then what you will found, first there will be Stokes line, then there will be, first it will be Stokes line, then there will be Rayleigh's line, and then there will be anti-Stokes line, if you consider in terms of frequency or in terms of wave number. But when you um, do it in terms of wavelength, then first there will be anti-Stokes line, then there will be Rayleigh line, and then there will be Stokes line. So Raman spectra, so in case of Raman vibrational spectra, what we found, in case of Raman rotational spectra, we found in this series, for original rotational vibrational spectra, it was the separation between the two spectral lines was 2b, but in case of Raman spectra, the separation between the spectral lines in a series is 4b. Suppose this is q, this is p, this is p, this is q, this is r. the separation between these two is 12b, that is 16b 16b, and for these spectra the separation is 4b. So it is different from the conventional rotational vibration spectra. The Raman rotational spectra, the separation between the lines in a series is 4b rather than 5b. So these are the things we discussed in this course. So I wish you all the best for your upcoming exam in this course. So thank you all. Welcome. Sure. Okay, bye.